And so we continue our journey with the basics of matter and energy in the second group of high school chemistry videos to talk a little bit about heat energy, which is a very important category within chemistry. First of all, what is heat? Well, heat is energy that is transferred between objects at different temperatures. So you put ice in lukewarm water and it becomes colder, and so forth. You put if you have a fever and you put a washcloth that has coldness on it, it helps cool off. And so one key aspect here that you know very well from everyday life is that heat goes from warmer objects to cooler objects. Cold doesn't go from cold to hot objects. Rather, hot objects gets the heat from a hot object gets distributed in colder objects. And so this process goes on until the temperatures of the two things that are touching each other or in proximity to each other reach a certain equilibrium. So let's say you have an air conditioner. I have some rooms upstairs, and one of those rooms has an air conditioner in it. I won't tell you which of my children has that room that they shut their door and they keep all that cold air to themselves. The rest of the upstairs the two other rooms has to be cooled down by a single air conditioner. And so it's much colder in the room that's closed with its own air conditioner than in the rest of the upstairs. But if we were to sneak up and open the door, then the hot air the energy, the heat from the hot would move into the cold, and eventually the entire upstairs would be the same temperature because that's what happens. It reaches a kind of equilibrium. So heat is a kind of energy that is transferred between objects at different temperatures until they're no longer different temperatures. Eventually the sun will burn out and will become of an equal temperature to the rest of the universe. Don't worry, nobody watching this video is going to ever be around when that happens. So the most common transfers of energy in chemistry are exchanges of heat. So there can be exothermic exchanges of heat. What you're looking at is the aftermath of an explosion of the Grand Camp. Grand Camp. It was a French ship that was docked in Texas, and it had an amazingly large amount of ammonium nitrate on it. And we don't know exactly why the fire started. Maybe somebody flicked a cigarette overnight, and by morning it was a problem. And when it exploded, it either destroyed or damaged everything in that little Texas port town. That's an exothermic reaction based upon a chemical reaction. It's not an atomic reaction. That's even worse. But this is the largest known chemical exothermic reaction and the worst industrial disaster in the United States history. Well, anyway, an exothermic reaction in which heat is given off in a chemical reaction. There are also endothermic reactions. Remember, exo means outside, endo means inside. So an endothermic reaction is where the energy is absorbed into something, such as when dough rises. That's an endothermic reaction where energy is absorbed into something. Well, so basically heat is the number one kind of thing given off in a chemical reaction. Okay, well, temperature. Temperature is a measurement of the average kinetic energy of the random motion of the atoms and molecules in something. This may seem like what does this mean? I mean, but have you ever wondered when somebody takes your temperature, what are they taking? We might say, well, we're seeing how hot you are. Do you have a fever? If you're running a fever of 101 degrees, what does that mean? Well, kinetic energy is the energy of movement, and our atoms are moving. There is something called absolute zero that I'm going to talk about later in this video. That's when pretty much nothing is moving. It's negative 273 degrees Celsius. I'm not sure what it is in Fahrenheit, which is the normal measurement every day. But basically, stuff's moving, and it's moving on a micro level, on an atomic level. Atoms and molecules are vibrating and moving around. And so as the temperature goes up, the amount of random moving around on that atomic level increases. So temperature is basically a measurement of the average kinetic, the average moving aroundness of the atoms and molecules in something. That's what temperature is. And the hotter something is, the more those atoms and molecules are moving around. Now, most people in common everyday America, at least, not in Europe, but in America, in the United States at least, most people measure temperature using the Fahrenheit scale. That seems to work fine for everyday kinds of things. So normal temperature is 98.6 degrees, Fahrenheit. Water freezes at 32 degrees Fahrenheit. When you put water on the stove and it boils at 212 degrees Fahrenheit, those are just a few, kind of Fahrenheit benchmarks. 72 degrees, some would say, is a perfect temperature for the human body. Not everybody agrees, of course, depending on where you grew up, probably. But that's not important right now. So temperature, Fahrenheit. However, in science uses the Celsius or centigrade scale because it's more precise. In science, you need to be precise. You need to and science has come up with these standard units and measurements of things. And so in science, we use Celsius. It's more precise. In Celsius, basically 0 degrees Celsius is the freezing point of water, and 100 degrees Celsius is the boiling point of water. See how that makes very nice kind of basis for a system. Rather than 212 and 32, you have 0 and 100. So the Celsius scale is more or less based upon the boiling point and freezing point of water. Now, how do you get from one to the other? This is something you might have learned before. There's actually a common sense to it, and so it's you don't even have to memorize these formulae. You just kind of can figure it out. So to get from Fahrenheit to Celsius, the first thing you need to do is get to 0. If 32 degrees is the freezing point for Fahrenheit, then if we subtract 32 degrees, then we've gotten to 0, so to speak. Then all we need to do is recalibrate into Celsius by the kind of ratio of a Celsius degree to a Fahrenheit degree. 5/9 is basically the ratio. So if you take 212 degrees where water boils and you subtract 32 from it, you get 180. 100 degrees Celsius is therefore 100 degrees is the same as the span of 180 degrees in Fahrenheit. And if you divide 100 by 180, you get 5/9. And so basically, to get from Fahrenheit to Celsius, you subtract 30 to get to 0, and then multiply by the ratio of Celsius to Fahrenheit, which is 100 to 180, or 5/9. The other way around is just the reverse. So to get from Celsius to Fahrenheit, you're going to get it to the proper scale. So you're going to this time multiply by 9/5, which is the flip of 5/9, and then you're going to add 32. See how that works? Very nice, very neat. So these are the conversion formulas. You don't have to memorize them because they follow a certain kind of common sense to get from one to the other. Okay, the Kelvin scale. You need to know in chemistry the Kelvin scale. This is what I was mentioning a second ago. Basically, if you add 273, well, technically 273.15, but if you add 273 to the Celsius scale, you get the Kelvin scale. Why would I want to do that? Why would I want another scale? Because the Kelvin scale takes us to absolute 0. Absolute 0 is the coldest temperature possible, negative 273.15 degrees. That is where all atomic and molecular motion stops. You can't really reach it in reality, but scientists have come to that conclusion by extrapolating back from what we do know about the motion of atoms and so forth. Okay, so the Kelvin scale is an absolute scale, starting from absolute 0 motion, to infinity and beyond. Last thing in this video sequence: what is the specific heat of a substance or compound. What is the specific heat? The specific heat is the amount of heat energy necessary to raise 1 gram of whatever that substance is by 1 degree Kelvin or by 1 degree Celsius. So what it turns out to be is that different substances have required different amounts of energy to raise their temperature. So if you put a metal pot on the stove, you'll notice that the pot gets hot a lot more quickly than the water inside the pot gets hot. Why? Because metallic objects tend to have a lower specific heat than water. Water actually has a fairly high specific heat, which is why it's good at putting out fires and things like that. Why water tends to be a rather stable substance, because it does not heat up nearly as fast as many other element or substances in the world. And so the specific heat of something is the amount of heat energy necessary to raise 1 gram of that thing by 1 degree Kelvin. And you can look it up. You can Google it online. You know, what is the specific heat of water? Or what is the specific heat of iron? And you can find out how much energy it takes to raise the temperature of that substance by 1 degree Kelvin or 1 degree Celsius, 1 gram of that substance. Okay? So it is measured in joules per gram Kelvin. And it is important, maybe I should do a video on the factor label method, because keeping track of the labels, joules, gram, Kelvin, is very helpful when you're trying to figure out things. Joule is a amount of energy. We'll just leave it at that. Don't try to understand it at this point, but just say that joule is the unit of energy used in this case. It's actually related to calories. Anyway, not important right now. And then when you say per gram Kelvin, that means that gram and Kelvin are multiplied by each other in the bottom. So if you have a fraction, grams and kelvins are on the bottom and joules are on the top. And I added at a constant pressure and volume because those can change the dynamics of how the heat rises. Well, that's it.